So hi everyone, I'm Mohini. I'm a PhD student at Berkeley and I work mainly with micro-PMU data, which is high resolution phasor data from distribution networks. And today what I wanted to talk about was to talk about a particular use case that is enabled by the NI for AI platform. And I hope that this will give you a sense of how easy it is to use the platform and to query and analyze the data, and also get you started thinking about your own use cases and applications. And the particular use case I'm talking about is voltage sag detection and analysis. So as you've probably gathered from the previous speakers, the great advantage of this platform is that it makes it really easy and even enjoyable to explore data, including very high resolution measurement data that can be quite intimidating just in its volume, and especially if it's being shared in other forms, like in a CSV. And the platform not only makes it easy to explore the data, but it also makes it easy to analyze data and to ask and answer questions of the data. And finally, it makes it easy to share results, whether that's in the form of raw data or scripts or anything like that. And I think the last part of sharing results is often overlooked, but this is really essential if we want to effectively share knowledge and if we want to build on the results of others and ultimately deploy real applications. So what I'm going to do here is demo the typical development process for one use case application, and that's voltage sag detection and analysis. And I'm going to walk you through the typical 4 steps that I can think of for analytic development in this particular case. So in step 1, we establish our motivation for this particular use case and the questions that we have. So we want to answer the questions, what are we interested in understanding and why is this important? Well, in this case, the what is voltage sags, and these are brief, significant dips in the system voltage. And what we specifically want to understand about sags is their frequency and their magnitude. And why we want to understand this is because sags can have a detrimental impact on the system, especially on sensitive equipment. And they could also indicate safety issues such as faults in the network. So here are 2 pictures that relate to the what and the why. The first picture in the top relates to the what, and it shows us a voltage sag. And this voltage sag is captured in point-on-wave data. So that's measurements of the time domain voltage signal. And we can see that the voltage sag appears basically as this reduction in the amplitude of the sinusoid. And the bottom picture relates to the why. Why is this an important thing to monitor? And what it shows is the tolerance of a piece of equipment to deviations in the system voltage. And the green region represents tolerable deviations. And what we see is that it constricts over the x-axis, so it constricts with duration of a deviation. And essentially what this means is that a piece of equipment can tolerate large sags if they are short, or it can tolerate long sags if they are very small deviations from the nominal voltage. And so really what would be concerning in the system is a very long and a very large sag. Okay, so now we've established our motivation, we can move to step 2, which is to explore this. And it's really in data exploration that I think the NI for AI platform really shines. And exploration is very critical for the development of new use cases and analytics. So oftentimes we get ideas from looking at the data, and these are ideas that we didn't have to begin with. And it's really difficult, in my experience, to develop an analytic blindly, that is, without seeing the data at all. So exploration is especially important for 2 reasons. The first is that we may be working with novel measurement types, which we're not very familiar with. So in the bottom left, we can see that novel measurements really make a difference in what an event looks like. So we see the same event in SCADA data, which is lower resolution, and then in high resolution PMU data. And we see that the event really looks different in these 2 data types. And so therefore, we really need to explore the data to get familiar with what new measurements look like. The second reason exploration is important is that we may be looking at new event types, things that we've never seen before, or things that have just been made visible by higher resolution data. So here we have on the right some voltage sags in higher resolution PMU, micro-PMU data, and we may not have ever seen this before in our lower resolution data. So those are two reasons why exploration is very important. So for this particular use case, I want to explore the data to understand what a voltage sag looks like. And what I really want to understand through this exploration is how can I automate the detection of voltage sags? Now, what I'm showing here is the Ping Things plotter, the visualization part of the NI4AI platform. And in this visualization, I can very easily find sags because there are these very distinct deviations in the voltage magnitude. And especially large sags are easy to see. And once I found a sag, I can quickly zoom in to look at it at much higher time resolution. So I can go from hours to seconds very quickly and really familiarize myself with the shape of these events. So looking at these sags, I understand that what I should really be looking for to detect sags is large deviations in the magnitude of the voltage from nominal. So that takes me on to step 3. So in step 2, I've got an idea of what I'm looking for and how I should look for it. And now I can automate the sag detection. And I'm going to do this in a Jupyter notebook, which Chris also showed you. And the great thing about the Jupyter notebook is that I can intersperse text and code and visualizations and really have a record of my work and exploration. So based on what I know about sags and based on my exploration of sags, I see that this sag, a voltage sag, is defined by voltage measurements below a certain threshold. And I'm going to develop an algorithm to detect sags in 2 parts. So in the first part, which I'm visualizing on the left, I'm going to find any points belonging to a voltage sag. So any points where the voltage is below a threshold that I'm going to specify. So for example, for this sag shown in red, in this first part, I'm going to return the set of points, all these gray points that are below my threshold. Now, after finding these raw points, I'm going to have a second part of the algorithm, which is going to aggregate these raw sag points into individual independent sags. And once I've aggregated these points, I can then determine the duration of the sag and its magnitude. So the reason I choose to construct my algorithm in these 2 parts is based on the structure of this very high performance database that's underlying the NI4AI platform. And this is what Chris introduced you to. And basically the main feature of the database is that it's structured like a tree. So at the bottom, in the leaves of the tree, I have raw data points. And as I move up the tree, I have these internal nodes that store these summary statistics of the raw data that lies below them. So this includes the minimum and the maximum of the data below that node. And as I go up in this tree, I'm getting to lower and lower time resolutions. So if I'm looking for extreme values, which is what I'm looking for when finding voltage sags, this structure makes it really efficient. I can look at a kind of large window, at the summary statistics over a large window, and consider the minimum in that window. And only if the minimum meets my criteria of being under a certain threshold, only then will I go down all the way to the high resolution raw data to retrieve the voltage sag. Okay, so what to show you is this video where I'm walking through my notebook, which contains the scripts to do this exploration of voltage sags. So let me play this. So just like Chris's notebook, I start out with some basic imports of the database and of the different Python libraries that I'm going to use. And this is the great thing about being able to query the data into Python. I can use all these great libraries that other people have made to really speed up my analysis. Then I connect to the database, which is very simple. I use my API key, which all of you can get by signing up for the NI for AI platform. And now once I'm connected, I can look at the different data streams in the database very easily. So in this case, here I'm querying a set of streams. And what I'm looking for specifically is streams belonging to this particular collection called the sunshine dataset. And I'm looking for voltage measurements, so voltage magnitude measurements. So I run that. It takes just a second. And now I can print the set of streams that it retrieves. And these are the set of streams that I've got. So I have this whole streams in the sunshine data set of voltage magnitude measurements. They correspond to multiple phases at several PMUs. And notice in these notebooks, I can intersperse text like this with the code, so I can explain my steps and my reasoning through this use case. So here I have the first part of my algorithm. So this is the function that is looking for those raw sag points. And you see that and I call this find vsags DFS. It's a depth first search function because it's looking through this tree structure efficiently to find those sag points. And the arguments to the function are just my start and end times that I'm going to be looking over. And this is the point with which Chris discussed. It tells me the kind of resolution, the level in that tree at which I'm going to be looking for some data. So the function is not very long. It basically queries some windows. These contain the statistics over these time windows, the summary statistics stored at internal nodes in the database, and this query is therefore very efficient. And then I'm traversing the windows to find either points or windows that meet my criteria of having voltages below a certain threshold. And you can see here that when I find those points, if I'm at a low resolution, I now go down in the tree. So I'm going into higher resolutions of data to find the voltage sags themselves. And if I'm already down at a very high resolution near the raw data, then I just return the points themselves. So these points are pairs of timestamps and values. And then what this function ultimately returns is a generator or an iterator of these raw sag points. So every point returned by this function meets my criteria of being below a certain threshold and corresponding to a voltage sag point. So that is the first part of my algorithm. I can run it. And now the great thing is once I've written the script, I can immediately test it on real data. And so here I'm testing it on 1 month of data, 2015, and I'm going to try to find a bunch of raw sag points over this 1 month. And I'm choosing a threshold of 0.9 of the nominal voltage. So that ran very quickly, if you noticed. And now I can look at, for example, one of the sags that was found, and it's retrieving the data of the sag, and there's that sag. We see that it's this very typical large deviation from the nominal voltage. So now that I finished the first part of my algorithm, and this is the second part. So this function is going to aggregate the raw sag points into individual independent voltage sags. And what it's going to return is basically the start time of the sags that were found, their duration, and their magnitude, which is the magnitude of the deviation from nominal. And the input to this function is the output of the previous function, which is this iterator, or generator over the sag points. So now what I'm doing is I'm looping through those raw points, and I'm basically checking if a new raw sag point belongs to a previous sag or corresponds to a new voltage sag. So if the raw point is more than 1 second away from the last sag point, then I decide that it corresponds to a new voltage sag, and I store the summary of the previous SAG and increment to start looking at a new voltage SAG. And on the other hand, if the new SAG point belongs to a SAG that I've already seen, then I simply update my values for that SAG. I increase its duration and adjust its magnitude. So I wrote that function and I run it, and now I can, again, immediately test it on a significant amount of data. So what I'm going to do is I'm going to test it on 1 month of micro-PMU data. So this is a large volume of data. This month corresponds to the end of 2016. And I'm choosing a more aggressive threshold of 0.98 of nominal to really get more voltage sags during this period. So I run this and it's looking over that month, and we see that it's running. I see that asterisk in the top left, and now it's done. It's finished running over that whole month. It took just over 7 seconds, and it found 4 voltage sags. And what I can look at immediately is some statistics of these sags. For example, I can plot the duration versus magnitude of these sags, and I see they're distributed in that way. Now I can run it on an even larger amount of data if I really want to find more interesting sags. So now I run it over 3 months of data. Again, keep in mind, this is 120 hertz micro-PMU data. So this is a very large volume of data, and I'm looking for sags over 1 PMU stream. Now notice I've chosen an even more aggressive threshold. Anything below 0.99 of nominal, I'm going to return. And so here is the first part of my algorithm. This is the function that's returning the raw sag points. And then I have the second part of the algorithm, which is returning which is aggregating these points into independent sags and return the start times, their durations, and their magnitudes. So we give this a few seconds to run. And of course, I've chosen a very aggressive threshold. In a real application, you would adjust that based on the sags that are of interest to you. So now it finished running and it found a bunch of sags, and I can again look at their duration versus their magnitude, right? This is of interest because it reflects how equipment may react to the sag, and I see that they are scattered in this way. And I go on lots of different analysis with all these sags that were found. So I'm going to share that with you in the slides. Okay, so this is what I showed you before. Here I have an example of a voltage sag that was found by my algorithm. And now I move on to step 4 of the analytics development, which is to answer questions that I have based on what I found out from the data. And so some questions that I have about voltage sags are, what are the magnitudes and durations of voltage sags at this particular location? How well does a model from the literature describe the frequency versus magnitude of the sags we observe? So as I said, the magnitude of the sags is important because it indicates how equipment may respond to these sags or how damaging they may be in our system. And we have a model in the literature that will describe the frequency of sags of a certain magnitude, and I want to validate that model against the data that I have. Another question I have is, do we see any impact of distributed generation on the sag magnitude? And finally, are there any weekly patterns in the sag frequency at this location? So I'm answering all these questions in my Jupyter notebook using those voltage sags that I found with my algorithm. And this is in answer to the first question, what are the magnitudes and durations of sags that occur at this measurement point? So I see here's a scatter plot showing the duration of the sags on the x-axis and the magnitude, the deviation from nominal, on the y-axis. Or sorry, rather the magnitude shows the minimum value in the sag in per unit on the y-axis. So these here at the bottom are much larger sags. And these sags were found over 1 month of data, so that's 300 million data points, and it ran very quickly. You saw that in the demo. So the interesting thing here to note is that I don't have any sags in the danger zone in this region, which is good. So on this system, I didn't see any large and long sags. So that's great news. Okay, so on to the second question. How well does a model from the literature describe the frequency versus magnitude of the sags we observe? So in the literature, there's this very simplified model, which makes a lot of assumptions, but tries to model fault-induced voltage sags and to predict the frequency of sags of a particular magnitude. And basically what this model says is that the frequency of a sag with magnitude V will be proportional to V over 1 minus V. So what that means is that we will have far fewer very significant sags and far more small sags from nominal. So the orange line is what the model would predict, this simplified model, and the blue is from my data. And what I see is that it looks pretty promising. Of course, I would need to do more analysis at more locations to say that definitively, but this model fits this location over the time period that I looked at quite well. Okay, on to the next question. Do we see any impacts of distributed generation on sag magnitude? So there is some theorizing in the literature that distributed generation, the presence of distributed generation may reduce the magnitude of sags at a location because the injection may hold the voltage up during a sag. And we can explore this through the platform because we have access to an open source database which includes measurements at an injection point of a PV installation. And so that is in the Sunshine dataset, which you can all access. And basically in this dataset, we have a PMU1, which is measuring at a PV location. We have another PMU at the substation above that PV injection point, and then we have PMUs further away on other feeders. And so now I ran my sag detection on all these PMUs, and I can look at the magnitude versus duration at each of those PMUs. And the stars correspond to the means at each PMU. And it does look like from this small experiment that the sags are smaller on average at PMU1, at the PV injection site, than at the other PMUs further away. Finally, I can look at the frequency of sags over days of the week and ask about whether there are weekly patterns in the sag frequency. This is made very easy by the platform because I can work easily with the timestamps on the measurement data and do this analysis. And at two different PMUs, I do see that there is some very distinct days on which I have more sags. That was the extent of my analysis of this. Of course, you could do more analysis to find out why that may be the case. So after answering all those questions and going through the steps of the use case development, the last step is to share my results. And in fact, the great thing is that this is very little extra work because I basically have something to share right away as the output of my analytic development. And that is the Jupyter Notebook, which has this code and text and images mixed together. And it's something which is very readable and which somebody else can run and add to. And that's all from me. So I'll stop sharing.